Hello everyone. This is fourth lectures on quantum mechanics. Today we are going to talk about the uncertainty principle, which is very important and very fun and very remarkable result of quantum mechanics. Here it is. So let's think about this wave with wavelength lambda. So the wave isn't precisely anywhere. So when someone asks at this moment, like this, question 1, where is the wave? Then the question may not be a good question. We cannot answer to that question since the wave doesn't have precise position in this situation. However, when someone asks like this, what is the wavelength? Then we can answer that question as lambda. And see this? How about this? Here is a bump here, sudden bump here, and this is also some kind of wave. And someone asked same question before. Now the situation is reversed. Question 1, where is the wave? We can answer that question like this at x1 here, right? And question 2, what is the wavelength? Now this question is not good question anymore, right? We cannot say about the wavelength in this situation precisely or accurately. So we can see that the more precise a wave's position is, the less precise is its wavelength, and vice versa. As you can see here, this situation, the wave's position is precise, however, the wavelength is not. In this situation, the wavelength is very precise, however, the wave's position is not. So we can intuitively deduce that the relation between the precision on the wavelength and the position. And this is the key center of the uncertainty principle by Heisenberg. So note that you must know this de Broglie formula. A particle's momentum p equals to h over lambda. P equals h over lambda. So spread in wavelength, which means the uncertainty in wavelength, is related to the notion of spread in momentum. Obvious. Since p equals to h over lambda, the uncertainty on p is corresponded to the uncertainty on lambda, right? So we can deduce this logic. Spread of lambda is up, the spread of lambda increases, and then spread of p momentum increases, and thus so is this sigma p. So statistically, the notion of spread or notion of uncertainty correspond to the notion of sigma standard deviation. So here, spread of p is related to this mathematical symbol, sigma p, also sigma x. And in mathematical representation, the Heisenberg's uncertainty principle is right here. The product of sigma x and sigma p is greater or equal than h bar over 2. It means that this is actually the inequality. So when the sigma x increases, the sigma p is reversely decreases. More easily, when the uncertainty on position increases, which means the uncertainty on position spread, which means the p uncertainty on momentum is decreases, so does the uncertainty of lambda. And this is exact what we've observed at the first in this picture. You got it. Yes. Let us solve one problem today. Here, a particle of mass m has the wave function psi xt a exponential minus a mx squared divided by h bar plus it, with a large A and small a is the positive real number. So first question is find a. So when a question asks you, you have to find the multiplicative constant of the wave function. What you have to do is just to normalize it. How to normalize it? Just integrate n equals to 1. So just integrate the probability density, norm psi squared, psi conjugate psi, and then integrate it, and then equals to 1. And that process is here. And now I think you are good at the Gaussian integral, like this. If you're not familiar with this Gaussian integral, just see the lecture 1 to 3 on my YouTube. So we got this a equals to here. Next question is, for what potential energy function Vx is the solution to the Schrödinger equation? So we have to recall this Schrödinger equation, I ha bar partial t psi equals to Hamiltonian psi, and then just plug in the psi, plug in the given psi. Alright, this is Hamiltonian operator, and then canceling out, blah blah blah. Then we finally get this form. This is the quadratic function, you know that. And when it comes to quadratic function, is the form of x squared is given as a potential. This is corresponded to the notion of harmonic oscillator. So this psi is psi obeys the harmonic oscillator's potential. We call this as quantum harmonic oscillator. Quantum harmonic oscillator. This is very important concept in quantum mechanics. For practical application, we can very roughly assume that a solid is a group of these quantum harmonic oscillators, which is precisely the notion of Einstein's solid. So the notion is very fun and yes, much of enjoy. So we will treat the notion for future in, I think, in lecture 12 or 13. Okay, next question. So calculate the expectation value of x squared, p squared. So we know that the sandwich method, when we have to find out this expectation value of some quantity, we just sandwich the quantities operator with integral guys here. Integral guys. Just sandwich them. You know, this x is itself is position operator, and then just calculate, but we can observe that this is of the form odd function, right? So by the symmetry of odd function, we can get 0 immediately. The next expectation value of x squared, blah blah blah. We get this. We also use the common Gaussian integral with application this when x squared is multiplied in front of this Gaussian. We know this trick. Just plug in lambda as here, here, 2am over half bar. Just treat this term as lambda. And we get this, and so on. The expectation value of p, you know that the operator of this momentum is minus I half bar partial x, and then we sandwich them with the sandwich guys, bread guys, right? In this case, we also get this odd function form. So the conclusion, the value is just 0, right? Lastly, we have to find this expectation value of p squared. Also, we just plug the momentum operator here and square it. We've solved this. You've seen this by the theorem in last lecture. When you have to find out some quantity in terms of the position or momentum, we just plug in the operator term in that form. So we just plug the p operator here and squared it. That's it. So blah blah blah, calculation is going on. And here we have to find out the second derivative of x of this exponential. Some kind of tricky, but you can do it if you know the simple calculus. And then we got this, and so on. And we again meet these guys, Gaussian guys, and we know how to attack these Gaussian guys. I think you just it's better to memorize the results of Gaussian integral. Okay, so just find out this result, and finally we get this am h bar. Last question is find sigma x, which means the standard deviation of x and standard deviation of p. And is their product consistent with uncertainty principle? So here we know that uncertainty principle statement is when you product the standard deviation of x and p, the value must be greater or equal than h bar over 2. Just compute it. We used this very useful formula to find out the sigma, which is square root of expectation value of x squared minus square root of expectation value of x. We got this. Similarly, we got this. And then when you find the product of these two, you get this. And this is very, very consistent with this uncertainty principle by Heisenberg. So we can easily check the Heisenberg hold in this case. Actually, this Heisenberg principle should hold in every case in quantum mechanics. So it's some kind of quantum nature. Okay, that's it. Today we've talked about a very important theory, the uncertainty principle by Heisenberg, which states that when you multiply this sigma x and sigma p, the value must be greater or equal than h bar over 2. And this is very intuitive in this picture sense, so I think we've got it. Okay, if you enjoyed it, please subscribe and like, and most of all, enjoy the physics. Bye bye.